Well, I might as well go back to here. I just did this trivial modification to the notebook to show a bunch of different loss functions, including the one that Srinivas pointed out, the Mish loss function, which apparently does really, really well. And you can see they all have something in common. That is, they all are sort of asymmetric with an increasing with a sort of a increasing branch on the right, and on the left a branch that either asymptotically goes to 0 or asymptotically goes to minus a half or asymptotically goes to minus 1. And so, you know, the Mish is the most complicated one. It has a little bit of a local minimum somewhere between -2 and 0. And then from there on, it looks pretty much like all the other, like the ReLU and so on. The bounded ones are tanh and sigmoid. That's the red and the purple, where they tend to limits of 1 on the right side and either and -1 or 0 on the left side. So it's just interesting to look at those and to try to understand why one might work better than the other. I still haven't figured out why ReLU, which is this green one, works so well by eliminating all the negative weights. Even all the other ones also, well, Mish and sigmoid also pretty much push the negative weights down. They approach 0 asymptotically, and then the CeLU and the tanh do give negative weights, do include negative weights. So in particular, I don't know why ReLU works well, and I don't know why Mish works well. And also, I noticed that, you know, all of these, you know, the advantage, the selling point of ReLU was that it was so fast because it only has, you know, linear branches. So all of these other ones, I mean, I thought that going, you know, they initially had sigmoid, they initially had tanh. We still use those, but in the old days, they didn't use ReLU, they used sigmoid instead, or tanh instead. And now we're moving to something like Mish or these other ones. They're still, there's the soft plus, the orange one. These are still compute intensive. So I wonder, you know, it seems like their advantage over ReLU that was demonstrated in that paper is only if you have unlimited compute time, I guess. And just thinking to myself and not knowing the answer, I'm thinking that when you go to NLP models, which are extremely compute intensive, I'm wondering if Mish is going to still have such an advantage as it had with the, you know, with convolutional neural nets, as in the paper shown by, referred to by Srinivas. Anybody have any thoughts on that?
Another point to mention is that when you're using Mish, you can't use like transfer learning.
Oh, you can't use transfer learning.
Not just Mish, rather, you're trying to replace an already existing activation by something else, right? So that creates the problem with, you have to kind of train from ground up if you swap out activations from what you already have until and unless you're building something from scratch.
Right, because pre-trained models will tend to have used ReLU, and so they'll have
mostly a ReLU, right? Exactly.
They'll have positive weights.
Not not just positive weights. The weights change based on this function, right? Now, if you suddenly allow negative values back in, then your weights are different for that network.
Oh, that's a really good point. So the pre-training has, you know, one of the hyperparameters in the pre-training is the activation function that they used.
That is important, yeah.
So that's a really good point. Thank you for bringing that up. Anyone else have thoughts?
This one that you've kind of missed out probably, like between the ReLU and the Mish, is like the leaky ReLU.
Yeah.
So that kind of, again.
Yeah, there's one of these that has, there's also an ELU. The leaky ReLU has a constant, you know, the left branch is controlled by a constant, but the ELU and this, I think the CeLU as well, you have to solve for those parameters. There's an extra parameter that controls what the left-hand side looks like.
And like you mentioned, ReLU is the weirdest of the lot because it's not differentiable throughout, whereas all the others that you have on there is differentiable throughout.
Yeah, and
Uh,
that's perhaps one of
really,
the advantages of Mish is that it's infinitely differentiable.
I think all of them are infinitely
Yeah,
differentiable other than rel, right?
yeah,
The advantage with mesh is that, again, on the negative side, it lets you creep in certain values. But again, yeah, there's no real easy understanding as to why that performs better.
yeah. I mean, the ReLU could be easily fixed by just putting in a little corner here. I mean,
Right.
you know, a little smooth corner instead of the sudden
Zero,
shift.
zero, right.
Yeah, and then it would be infinitely differentiable as well. Okay, well, if there are no or other questions, we can move on. So the fashion MNIST data is apparently 60,000 training examples with 28 by 28 images. And surprisingly, you can get a lot of resolution. I mean, it looks surprising to me that in a 28 by 28 image, you can really tell what these pieces of clothing look like. So, so we just proceed in the way that we normally do. So here's, once you've got your TensorFlow installed and everything, you can check it, check that you have the latest version. You can import the data set, which is one of the Keras data sets. These are the steps. You train, you look at the training part. Um, it's unsigned integers, so the numbers are all unsigned integers, and split them. You can split the data set into. So you first import as I think it's just X train full, Y train full. That means getting all the data. Then you split off that into validation and training, and then let's see. I think you automatically get a test set also when you do this line, right? So we have our training set, we have our validation set, and we have our test set, and then you scale all the values, the unsigned integers, making them go, and the unsigned integers are between 0 and 255. So by dividing them by 255, you put them all onto floating point scale of 0 to 1. I'm not sure why they do that, because floating point takes more storage, but let's just go with it. You can then look at one of the examples, and the color map just is 0 or 1. I mean, sorry, binary, I guess it's just a grayscale. You can look at the training examples. They're all numbers between 0 and 10, sorry, 0 and 9. And these are so they're t-shirt, top, trousers, pullover, dress coat, sandals, shirt, sneaker, bag, ankle boot. These are the 9 items, 9 different classes of items. And in this data set, every class is unique. So you can't, you can only be one of those things. You can't be more than one of them. Okay, so let's look at the shape of the data sets. They're 28 by 28, 5,000 examples, 28 by 28 pixels. So then you can look at a bunch of examples, and there they are. It's kind of amazing. In 28 by 28 pixels, you can actually see a lot of detail. You can even read some words on them. Okay, so here's the thing. So this is all old hat. We've done this before, importing data sets, looking at them, and so on. Now we're going to do what's new. We're going to use Keras, the interface to, with the Keras gives you a sort of a very intuitive way to build models and then execute them using the TensorFlow backend. So, first you define a model, a sequential model. Sequential means you add layers one at a time. And so that's what this sequential API is. It's a way to build a model one layer at a time. And so it's very intuitive what you're doing here. The first thing you're doing is you're flattening the two-dimensional images into one-dimensional vectors. And you don't have to tell, all you have to tell it is the input shape, and it knows what to do from there. The next thing you're doing is you're adding a dense neural network layer. That means a fully connected layer with the ReLU activation function. And again, here, all you have to do is tell it the output shape, and it knows what to do to get from a 728 vector to a 300 vector. And the second layer, you're adding another fully connected layer on top of that that brings you down to, narrows you down to 100 outputs with a ReLU activation layer, a ReLU activation after it. And then finally, you can sort of understand what you're doing here. You're now narrowing things down to a vector of length 10. And you're picking, here's where you get the class. You're going to get probabilities for each class with the softmax activation function. So what comes out is, you can have a predict proba that gives you the probabilities for each of the 10 classes. And then a predict function will basically just pick the one with the highest probability and give you, and actually make the classification. So, so once you've built the model, you can then look at the layers to make sure that they're, oops, I didn't do that. I have to run this. Do this, and I can see that the layers are what I wanted them to be, a flattened layer, a dense layer, and a final dense layer. And then we're backing up a step. When you run your model, you might want to tweak it, and then you might want to run it again. So in order to initialize everything back to 0, in order to sort of destroy the model that you've already created and start from scratch, you have to do this keras.backend.clear session. Backend is a bunch of utilities, and clear session is one of them. So I opened up all of these keras. So the keras has its own web page, and there it is, and it has getting started guides. It's got a lot of good documentation. And so one of the things was the back end. It tells you what the back end is, all the different utilities you can access. And we're just right now from back end, all we're doing is using clear.
Hey, can I just jump in and say something?
Certainly.
From practical experience, and I really hope that they have addressed this in TensorFlow 2. I've been working more with PyTorch lately, but this backend clear does not always work. At least not the way you think it does. So just be cautious. I have had to, restart notebooks multiple times. You get, a clear slate. So if you're finding your results are funky and you're running things over and over again in a Jupyter notebook, it might be better to kind of exit out and start it up again, just because that backend clear does not necessarily always work, or at least it didn't as of Keras 2.23.
So if you do model equals none, does that work? Like, to start fresh?
It was kind of like hinky.
All right.
It was a problem. I think it was like, more of a problem in the multi GPU, but yeah, I have comments on the GitHub under that area that I follow, and it doesn't seem to have yet been fixed, but I don't know.
Okay. Okay, so now we back up and we do this clear session, and with and remembering, what Stephen said, we may find that this sometimes doesn't work, but right now it seems to work fine. And then we build the model again, and we could have done something different here. We could put another layer on it or take one of the layers off or whatever. This is a place where you can make changes once you clear the previous model. So I've done that, build a new model, check the layers again, and then we can look at this nice function called model.summary, which not only lists the layers, but it tells us the shapes of them and the number of parameters they have, the shapes of the output, that is, and the number of parameters they have. And as you can see, and as he points out in the book, the dense layers tend to have lots of parameters, not surprisingly. And this one has 1,010 parameters. Does anybody know why this has, see, the last layer has 100, and this layer has 10. So wouldn't you expect the output layer to have 1,000? Why does it have 1,010 parameters?
For bias.
The biases.
Yep, there's 10.
Yeah.
There's 10 bias parameters that have to be solved. And that's the same reason why this isn't 30,000, it's 30,100, because there are 100 bias parameters to be solved here. Okay, and then another nice utility is this plot model that gives you a schematic representation of your model, what the input looks like, what the output looks like. Here, the question mark is just the number of examples you have. So input, output, the flattened layer has an input of 28 by 28 and an output of 784, as you expect. The dense, all you told it was the output, but it knew that the input is 784. So it builds the right matrix, the right weight matrix to make that transformation. Here again, the output is going from the input is, the output from one layer becomes the input for the next layer, right? So the input for dense 1 is going to be 300, a size 300, and the output is going to be 100. And then the final layer, the output of this layer becomes the input for the last layer, and we're narrowing it down to a vector of length 10, one for each class. So this all makes sense to everybody, I hope. We've got two hidden layers, one hidden layer, because this is just, no, there's two hidden layers, sorry. The flattened layer is the input. This is a hidden layer, and this is a hidden layer. So this is a multi-layer perceptron model, and then this is the output layer. Okay, then there's this model.layers where you can list the names of these layers. Okay. And now you can get out the, so there's a method on hidden. There's a method that allows you to get out the weights, the weight matrix. And so this is how you do that. And you get the weights matrix, and you can see that it's 784 by 300, which is what you'd expect. And you can get the biases. They're all zeros apparently at this point. And bias vector is of the length 300. Okay, I kind of added this to try to play with learning rate schedule, but I didn't really get any better result than Jerome had. So let's just skip that for now. I'm just doing what he did here, just a straightforward compiling the model by giving. Okay, once you have a model, you compile it. You have to supply this is just like in PyTorch. You have to supply a loss function, an optimizer, and tell it what metrics you want to use. So in this case, we're going to use sparse categorical cross entropy, because our pixels are, the space of 784 pixels is sparse. Not all possibilities are going to be realized. Images have special spatial relationships, and so it's not going to be sort of randomly, spread over 28. The training data is not going to be some random set of 28 by 28 pixels, because images are special in that they have spatial relationships, and so that's why you get to use sparse categorical cross entropy.
Joseph, the loss
yes.
is to do with Y, right? So it's nothing to do with the image per se, right? It's just that you have 10 classes and they're one not encoded.
Is that right? Okay, so the 10 output, okay, right. So what Rekil is saying is that because we don't have, we're not allowing multiple classes, we're only allowing a single class for each example, then each of these vectors of length 10 is sparse, because only one of the entries can be different than 0. That's the point you're making, right, Rekil?
Yeah, at least that's what I think, because loss is just looking at the output, right? Y hat versus Y.
Yeah, you're correct. So that's how we would compile the model. Now that the model is compiled, you can actually fit the model. The next step on the training data. So I did that. I mean, that takes just a few minutes. By the way, I run it on my own machine, and I'm getting like 100 microseconds per sample. What are you getting when you run it on Colab? Anybody?
It says 2 microseconds per step. I don't know if it's the
Wow.
same.
I
but
get 3 microseconds per step, but I ran it on a TPU just for kicks.
A TPU, okay. Wow, my machine is slow. All right. Okay, so we got this so we fit the model and we call it history. So then we can look up what we got available in history. We got a lot of private variables, but then we have a lot of other methods and so on. These, I guess, we're going to explore in the rest of the chapter. These look like callbacks to me. The main thing we're looking at here is probably the parameters and the model and the epochs. So let's look at the parameters. We have a batch size, we have an epoch. This is basically defines the run that we just did. We're using validation. We've shown what metrics we're using. The epochs, there are 30 epochs and they're listed here. And then if we look at the history is a dictionary. You can look at the keys and you get, let's see, I think I didn't execute this stuff. Let me execute it all. Let's see, I did that. History parameters, history keys. So all we have is loss and validation loss. I thought I had more keys before. Anyway, let's see. So now we can just, this is really slick here. You can use pandas to plot this history dictionary. There is supposed to be more than one, more than something. Somehow I'm missing some keys. What did I do wrong? Must have done something. I'm not going to run this all over again. I know. I was running the regression model before, so okay, bear with me while I run this again. I have to do that. I think I did this part, but I'm not going to do this. Do this, and now I'm going to see. I had in my history, I had run the regression model from the next section, so that's why I have to run this again. It doesn't take that long, a minute or so. So let's keep going and see what this plot's not going to be what I want. So I guess we do have to pause. So while we're waiting for the few minutes that it takes to run that, are there any questions we can answer? We can discuss. Any items you want to discuss?
So I just want to say that pandas is the greatest thing since sliced bread.
I know.
I'm amazed by how good it is. I've gotten into it this week like hardcore, and I was just like blown away.
Yeah, especially in that plot where you tell it to plot a dictionary and it knows exactly what to do. It plots, there's going to be 4 different plots and they're all going to be labeled. And all you told it to do was plot the dictionary. So yeah, that's pretty amazing.
Okay, bone I'm picking with Jaron is that he says that we should be shifting the validation curve a half an epoch, yet he does not do so in the graph.
No, he doesn't, but he explains why you have to do it, and that's enough, really. I understand what you're saying. You can do it yourself, though.
I know.
And see how it looks. But yeah, so he points out that the blue curve, the training loss is, well, the validation loss is lower than, looks like it's lower than the training loss at the beginning of training. And he explains the reason for that. Which is that the training loss is computed on the fly at mid sort of, so it's computed from a moving average. So the time to be assigned to each epoch is kind of like the middle of the epoch. So that's half an epoch. Whereas the validation loss is predicted at the end. It's not, it's already, they don't have to wait. So So the training loss is basically earlier than the validation loss, and that's why you have to shift it. You have to shift it to the right shift it to the left in order that it be lined up with the validation loss. And if you did that, you would. This is the wrong two curves, but if you did that, you would see that the blue curve lines up better with the orange curve if you shift it by half an epoch to the left. We'll see that when we're almost done here. Any other comments? Let's see. Mosh wanted to discuss the zoo of activation functions. Sorry, Mosh, I didn't see that before. Have we discussed it to your satisfaction, or?
I think we're well past it. It's fine. Thank you, though.
Great. Okay. Yeah, activation functions are basically hyperparameters, and I guess it would be fun to play with, try to make your own and see if you can do better than the Mish. But I think people have spent so much time doing these, like there's the Swish and there's the Mish and there's this and that. They probably, it's probably not worth trying to find a better one because people have already spent so much time doing it.
We could put AI to work, maybe a GPT-3 run if anybody has a chance.
Yeah.
I'm kidding.
No, I mean, no, you're right. I mean, maybe it would find out something better. You could just tell it to construct a piecewise activation function and give it all kinds of possibilities and turn it loose and see if it comes up with a better one than Mish. Yeah. Okay, so we're done. Let's see. We have this history object now, which is basically the model. And again, you see all of these. These are callbacks that we're going to learn how to use them later. But right now, we want to focus on the parameters, batch size, epoch, steps, samples, blah, blah, blah. We can look at the keys. Oh, and look at the keys. And this time we should have, yeah, now we have the training loss, the training accuracy, the validation loss, and the validation accuracy. And this is what Stephen was saying, how slick Pandas is. PD.dataframe, history.history, that's the history.history is a data frame. So all you have to do then is chain this command plot. And it knows exactly what to do. I added a couple of, I added a grid and I added, oh, I don't think I added, this is what he did. So yeah, so you do this and boom, it knows what to do. It plots each item in the dictionary with its own label. And isn't that amazing? And then you can see that if you shifted the blue curve to the left by one half an epoch, sorry, it would be more overlaid with the green. And everyone knows why eventually the green lags behind. It doesn't decrease as much, right? The green is the validation loss, and it will generally never be as good as the training loss, as long as you're not under training. Okay, so the next thing you can do is you can evaluate on the test set so that you can then check your accuracy. And let's see, microseconds per sample loss. Okay, so 0.3 microseconds per sample. I'm not sure what that means. Maybe that means the loss. And the accuracy is 86%. I'm not sure why these numbers are different. Does anybody have a clue? Why are these numbers different? Here's the end here. It's 78 microseconds per sample. Okay, so that part makes sense. But now it says loss 0.3282, accuracy 0.8685. And I'm assuming that's the, that's the test accuracy and the test loss, but then it gives you these two numbers and they're not the same. At least the first number is not the same. So I'm not sure.
Are you complaining that the numbers?
I'm complaining that this number
different
isn't the
than-
same as this number, which is the loss.
My numbers on my collab are the same.
Oh, okay.
And yeah, I mean, again, I think this is partially has something to do with when you're running this on your own computer. Are you running on collab or are you running it on your own?
I'm running it on my own machine.
Okay, so when you're running it on your own machine, what I think happens is that because the graphics card also uses graphics memory and it affects your GPU slightly. Okay, so I noticed that when I run these things on the collabs, they're a lot more reproducible than when I run them on my own systems. So what I've been kind of doing is, I have two GPUs, so I'll just, throw it to one of the GPUs that's not using the display, or I'll make sure to like not fool around with my screen because I have noticed that that actually affects things.
That's a weird because that's a large
No, it's
effect.
not.
It is
It's-
weird. I mean, if it was
it's
just a few decimal places, I would think, yeah, that's no problem. But it's actually, that's like a better than 10% difference. So
Maybe I was lucky, but I have the same numbers and I'm running locally.
yeah, that's what So Stephen says he has the same numbers. You say you have the same numbers. So now I should be worried about my machine, I guess. Anyway, okay. Well, let's just keep going because I don't think this is really a serious problem. So now you can predict on the first three examples, and you can look at the y-proba on the first three examples, and notice that let's see, there are different numbers, so that it is getting a probability. It's just that these examples, it's very sure what they are. Rounding them off to 2 decimal places. Actually, what if I don't round? What if I leave it as 6 decimal places? Yeah, there we go. So now we have all these probabilities, but it turns out that they're very small except for one of them, because these three particular examples are apparently easy to classify. So an ankle boot, whoops, got to do this. Predict on the classes. Ankle boot, pullover, and trouser. Those are the 3 examples. 921 are the classes. I guess I did this already. Yeah. Anyway, you can now show them what they look like. Boot, pullover, trouser, and that's it for that example. You can do a lot of investigations if you wanted to, plot a lot of things and see which items didn't get classified correctly, look at what the confusion matrix is. These are all things you could play with. But anyway, so at this point now you've run a real neural network model using Keras and TensorFlow, not scikit-learn like we did last time. Questions up to here. All right, it looks like everybody's up. So the next class of problems that we deal with, the supervised machine learning problems, are regression problems, where you're trying to solve a continuous vector. In this case, it's just a continuous scalar. You just kind of estimate a housing price. So we've worked with this Boston. Oh, this is not the Boston housing data set. It's the California housing data set. Uh-oh, I looked up the Boston housing data set. So let me just look up for a second the California housing data set so I make sure I understand. Because I'm pretty sure that the prices are in hundreds of thousands of dollars. Okay, so what does it look like? Median house value measured in US dollars, but I don't think it's measured in US dollars. I think it's measured in hundreds of thousands of dollars. Oh, it even says this is the data set used in Aurélien Geron's book. So this is actually a data set that he curated, somehow made available on Kaggle for everybody. Median income. Oh, maybe the median income is in tens of thousands of dollars. Median house value, I don't see, okay, if you look at the histogram, you'll see that it can't be dollars. So going back to, we'll do the usual thing by importing the data and splitting it and scaling it just like we are used to doing. And we're not doing anything special. We're not, okay, we are scaling it. Aha. So we scaled it, but when we predict, it should know what we did in the scaling and it should scale it back. So here we go. Okay, so this is the deep learning part. We build a model with the sequential API. The first layer is a dense layer with a ReLU activation, and shape. You have to tell it what the shape is going to be. So you tell it that the input shape is 28 by 28. That's what this is telling you. If you look at xtrain.shape, that's going to be the from 1 to the end. See, the first dimension in xtrain.shape is the number of examples. And the second dimension is 28, and the third dimension is 28. So from the index 1 onward, that means 1 to 2, it's basically 28 by 28. That's what this thing is telling it. Okay, and so this one has only a single hidden layer. That's this one, and then the last layer is the output layer, which is mapping everything into one scalar number, floating point number. So then you do the compile again, telling it what loss. Again, remember the first step is to build the model layer by layer. The second step is to compile the model. And when you do that, you have to tell it what the loss, you have to specify the loss function. And remember, for regression problems, that's usually going to be mean squared error. You specify the optimizer, which is going to be SGD, stochastic gradient descent, with a learning rate of 1 times 10 to the minus 3, which seems to work well on, as a starting value in a lot of different problems. So then you fit the model. So first step is build the model. Second step is compile the model. Third step is fit the model. Fourth step is evaluate. And then fifth step is predict. So this is all what Jeremy is really proud about FastAI, that it does this in a, in a very small amount of text. Well, you can do that in TensorFlow and Keras as well. Okay, so FastAI is not the only flavor of machine learning environment to work in. So it's nice to see how things work in TensorFlow and Keras as well. So we do that. Let's see. I think I did all of this stuff. Boom, boom, boom. It's very fast. We're going to do 20 epochs. While it's running, does anybody want to offer any comments or observations?
Yeah, Joseph, can you hear me?
Yes.
The thing you were saying earlier, it's the rows, it's the columns, right? It's no longer the 28 by 28 images. It's more the columns that you supply of the data set as the input.
Yes,
So
I'm sorry. I misspoke. Yeah. So, yeah, this is the housing. This is going to be the features. Sorry. Thank you, Srinivas. Yeah, we're looking at the housing data set now, and it's basically going to have a bunch of features. It's going to be a two-dimensional table with number of examples, rows, and number of features, columns. And we can go over here while we're to see what the columns are. You've got 10 columns. So the data is position, longitude, latitude, median age of the house within a block, and that would probably be in years. Total number of rooms, I guess, I don't know what that means within a block. Let's see. No, these are houses. I'm not sure why they specify within a block. Total bedrooms within a block. These are all just features of houses. Total number of people residing. Maybe this includes apartments and stuff. I'm not sure. Total number of households residing within a home. Okay, right. So this is the, I guess the basic unit is a building, I guess, or the basic unit is a block, and that could be a building, or it could be a group of apartments, or a group of buildings, I suppose. Median income for households within the block, measured in tens of thousands. Median house value for households within a block, measured in US dollars. This I don't know how to understand, because if these are apartments, I mean, I'm assuming that I'm assuming that it's possible that you're renting the unit rather than owning it. I suppose you could still prorate it. If you have a building full of apartments, you can probably figure out how much each living unit costs. Anyway, so those, and then ocean proximity, which in California is a big deal, location of the house with respect to the ocean. All right, so those are all the features. And so there's 10 features. And now we're done. So let's see. At the end, it gives us a mean squared prediction error of 0.42. Now, that's a square of the price. So if you want a more meaningful number, you'd calculate the RMS prediction error on the test set, which is basically just the square root of that. And I'm assuming that we're in California, so it's got to be in hundreds of thousands of dollars. Because look at the data. Actually, I made this incorrectly, thinking it was the data. So if you plot a histogram, you can see that that's got to be in hundreds of thousands of dollars in California. It's not going to be in dollars. Yeah. So the thing that stands out to me whenever I work with these housing data sets is how bad these models are. I mean, $64,000 out of a few $100,000 is like a 30% error. It's not a really great, but I think that housing models just aren't that good. So I don't know too much about what the state of the art in housing models is, but it seems to me that a 30% error is pretty much rubbish. Okay, and so here's the end result, plotting the loss versus the epochs, and here you can see that. Sorry, the loss versus the loss versus the epochs for both the training and the validation data. Now, why didn't it know like it did before? Why didn't it have the label? Maybe. Anyway, the previous plot knew what all the labels should be. This one doesn't. So I'm not sure why. I added these. I added these labels. The x-axis is the number of epochs, which is weird because it shouldn't show half units. Somebody should, I should probably fix this and make sure that it only shows integers, but that's the way it is. And then loss is, this loss function that we're using, which is the mean squared error loss.
I still don't understand this 0.5 epoch, why that shift is. Could you print out what pd.dataframehistory.history is in a cell? I would imagine that epoch should be still the integers, right? So why is it plotting it like this?
So what's your question again?
Why is there, so when you plot basically pd.dataframehistory.history, there is a column for the x-axis, which should be integers, right? Running from
Yeah.
0.
Well, it's plotting them. I mean, there's nothing wrong with this plot. It's just that the labels, we would like to fix the labels so that they're integers. I mean,
there was a previous question and that was brought up that you need to shift it by 0.5, right?
Yeah.
Why?
0.5 why is and the reason that he gave is that during training, which is the blue,
Mm-hmm.
you're doing a moving average. You're computing a moving average. So, you're doing the stochastic gradient descent, right? So you're doing it one at a time, and you're updating as you go. And so, the value you get at the end, it doesn't care about all the iterations that went before. It's just going to give you the last value at the end of that epoch.
Right.
Right. Now, but that means that it's the actual time that should be assigned to that value is the middle of the epoch, which is half an epoch to the left. And so, whereas with the test set, you don't have that. It's the numbers are actually corresponding to where the actual number of epochs. So yeah.
Would it be right to say that if you were not using stochastic gradient descent and using gradient descent, the whole thing at one shot, then we wouldn't be seeing the shift?
I have to think about that. That's a good question.
No, you would still have to shift it, because for the validation set, you are evaluating it after the model has been updated with the good weights, whereas for training you are evaluating it at that point of time, right?
But you're still returning one value, right? That's why I'm not able to understand.
Yeah.
No, like so assume, so like you're doing it batch wise, right?
Right.
So so what happens is, after you do the model updation for that batch, I mean the weight updation looking at that batch, then you evaluate it on the validation set, right?
Correct. You'll get a loss.
If you were to evaluate on your batch with that updated weights, only then it's fair to plot them on the same along the same curve, right? Like, did you understand what I'm saying?
So you said you do one batch, you'll update the weights, right? At this moment of time, you
and then the validation set gets to be evaluated on the updated model, whereas for the training batch, you are evaluating it on the model that's not as good yet.
I see. Okay.
So the way he says it on page 305, if you have the book or under training and evaluating the model, it's right underneath that graph. Right underneath the graph, he says that on page 305, he says, but that's okay. In this particular case, the model looks like it performed better on the validation set than on the training set at the beginning of the training, right? Right, the green curve is lower than the blue curve. And he says, but that's not the case. Indeed, the validation error is computed at the end of each epoch, while the training error is computed using a running mean during each epoch. So the running mean, the running mean sort of corresponds to the midpoint of the epoch. And that's why it has to be shifted to the left. That's why the training error has to be shifted to the left.
Yeah, so if you were to compute the training error again using the updated model on that batch, then it would be a fair comparison between training error and validation error.
In other words, if you were to predict on the training data, yeah. Does that make sense, Rekil?
Yeah, I'm just wondering, like, how come when we do it in other things, we don't see this? Like, is there something specific with Keras? It doesn't sound like it. Sounds something which should hold with any training of the model, right? Like wherever you train it, PyTorch or FastAI, anywhere.
So we're probably, all of us are probably most used to, all of us except for Stephen maybe are, no, even Stephen, I guess we're used to using PyTorch and FastAI. And maybe there's something different about that. Maybe they do the correction or something.
But I think this phenomenon of seeing a higher validation accuracy for the first epoch is common, right?
Oh, have you seen that? Is that
I
something
think
you've
so,
seen before?
yeah.
Okay.
I see.
Okay.
I got to be honest with you. I don't think it's, it kind of matters. I mean, if you're overfitting or if you're fitting on the first epoch, you're doing something wrong. I mean, at least in my experience, I think if you're, we're looking out toward the, the 10th or the 20th or the 30th epoch, depending upon if we're using transfer learning or not, or how complex we're fitting something. And, it's kind of like, it's an interesting intellectual exercise, but I don't think it's that important, to be honest with you.
Well, still, I mean, when you look at the graph, you're sort of startled because you think, am I underfitting? Is my model wrong? Because, right, the training error is worse. It looks worse than the validation error. So I think it is important to straighten that out and understand what's going on. And I think that with Jeroen's explanation, we do know. In other words, if you were naive and you didn't take this into account, you would think, well, there's something weird going on because my model is underfitting at first. So maybe I did something wrong. But with Jeroen's explanation, you realize, nope, it's fine. Don't worry about it. Nothing to see here. Move on.
Well, validation error being lower than training error doesn't really show underfitting, right? Underfitting should be independent of anything else. It should just be the training error.
Well, isn't it when the training error is, when the validation error is
But if your
better than the
model is
training?
good on the validation set, it doesn't show underfitting, right? I mean, it should not depend on anything to do with the validation set. It should just be training error. I mean, if it does good on the validation, that's a good thing, right? That's always a good thing.
No, but logically, it should never do better on the validation set than on the training set. So something's wrong if your model is doing better on the validation set.
Underfitting. I don't think it indicates underfitting.
Okay, then maybe I'm wrong, but I think it does. Maybe we can continue that offline.
Sure.
So this is Rekil, right?
No, Gautam.
Gautam. Okay, so Gautam says that training set performing worse than the validation set doesn't indicate underfitting. So that's an interesting side discussion that we should probably resolve in Slack afterwards. Okay, let's see. Okay, so now it comes to the point where you can play with this yourself and try different things. We are getting close to. He says we should be getting close to. Well, actually, I skipped that part with the other model. Sorry, let me just rewind back to the. I'm not going to run any of this stuff, but back to the fashion MNIST. After this point, this isn't really the end. This can be the starting point for your own experimentation, and try to do better by trying different. And he gives you sort of a roadmap for how to proceed to if you want to improve your models. And this is something that everybody needs to learn how to do. So it would be worthwhile playing with this. First changing, he gives you sort of a roadmap on page 306. The first thing you want to do is change the learning rate. So you can play with that, see if you can do better, because the default learning rate is 0.001, I believe. You don't even see that because this code is so slick. It just a few lines of code and everything works. But in this model, we actually did specifically specify the learning rate is 1,000th. But in the previous model, where we're doing the classification model, he didn't specify the learning rate. It just got done automatically. It got set automatically by default. So let's go back to where he did that. That was here. These this one line of code that compiles the model, you just tell it the loss function, you tell it the optimizer, you tell it the metric. You don't tell it the learning rate because there's a default with SGD is 0.001. So, but if you wanted to, you could actually specify a learning rate here. So I just tried this little thing here by using a learning rate schedule that goes as 1 over time. And so far, I haven't been able to do better than just a straight learning rate of 0.001. But anyway, so, you should, this is the point where you should back up and try some experiments to try to do better. You can change the optimizer. You can, there's different optimizers available. There's a page with all the optimizers you can use. this tells you how to do the learning rate decay. So it has, you know, the usual optimizers like atom and momentum and all that good stuff. You can try different optimizers. You can try changing the number of layers. You know, we have 2 layers in this classification model, but you could make 3, or you could take one of them out, see what happens. You can change the number of neurons per layer. You know, we had 2 hidden layers, one with 300 neurons and one with 100 neurons. Those numbers are hyperparameters. You can change them and see if things go better. And then the other thing, of course, is batch size. You know, again, batch size is defaulted to 32. I always remember Jan LeCun's quote. It says that friends don't let friends use batch sizes larger than 32. So 32 is the default for batch size. But again, you can try different batch sizes and see if your performance improves. So I think this is a really important part of this little bit on page 306 where he sort of gives you a roadmap for how you could go about twiddling your model, because that's what you're going to do. That's what you're going to spend a lot of time as a data scientist doing is improving models and making better models.
Question, I have a good question.
Sure.
Is there a good reason for not using larger batch size other than GPU size? I mean, memory problems.
The only thing that I can think of is that you kind of lock things in too soon, maybe. By the bigger the batch size you use, the less noise you have when you estimate where the step should go, right? So if you are heading towards, suppose you're going downhill and heading towards a local minimum, then the bigger the batch size you use, the more confident it is that it's going in the right direction, and it's going to take that step. It's going to keep taking those steps that are very that are less noisy, because you have so many, you know, you're averaging together so many examples, right? The more examples you average together to make your updates, the less noisy those updates are. But in some sense, if you're dealing with a loss landscape that has lots of local minima around, and you want to get to the global minimum, you kind of want to shake it up a little bit. You don't always want to go in the best direction, right? So noise is good as your friend in that case. There's a sweet spot. You can imagine doing SGD, just stochastic gradient descent, which is just doing one example at a time. That's the sort of the extreme with the noisiest, you know, the noisiest estimates, right? And the other extreme is doing all of it at once with, it's just called gradient descent. Just run all of the examples through the, you know, through gradient descent all at the same time, right? Those are the 2 extremes, right? So you might imagine that there's a sweet spot somewhere in there, right? Somewhere between 1 and, you know, 50,000. There's a sweet spot that gets you a better result, and you can find it by hyperparameter tuning.
Hey, Joe.
Wait, I want to just check if Gautam is satisfied with my answer.
Yes.
Okay, great. Yeah, Steve.
Can I just interject something about the batch size?
Sure.
So regarding the batch size, one of the problems with small batches is that if you're using an algorithm which uses batch norm, as most advanced algorithms do, with a batch size of under 16, the batch norm algorithm starts breaking down. So in experience, 32 is kind of the lower limit of what you should be using for a batch norm. And I have actually used higher batch sizes with batch norms if if things can permit it. I think that the combination of the batch size is also relative to how many, samples you have. If you're running, somewhere around 20,000 or 30,000 items, in your training set, and you're using a batch size of 128 or 256, that's fine. If you have only 1,000 samples and you're running a batch size of 256, that's not okay.
Right.
So again, everything is kind of relative, but particularly, with batch norm, you do have to be mindful of the size of your batch. And if you can't do a batch that is large enough, you should not be using batch norm. And I have, in those circumstances, used group norm to actually good effect, and I would recommend that.
That's an interesting point. Do you mind writing that up and posting it on Slack?
Sure, no problem.
Great. The elephant in the room, of course, is how much memory you have available. I mean, you might want, it might be true that, like I said, the sweet spot is somewhere in between 1 and the number of samples, right? The sweet spot might be 1,000 samples. It's usually a multiple of 8, by the way, but so 1024. But that's fine if the sweet spot is at 1024, but it doesn't do you any good if your machine can't fit 1024 examples in GPU.